And now we're going to move into regularization, do an experiment with regularization. For this, you need to install a package called CAR, and we're going to be working with a data set, the prestige data set, that computes a prestige value for different professions. So we're going to have, for each profession, we're going to have different measures, like what's the percentage of women in the profession, what's the income, um, and different types of features that we are going to use as predictors for the prestige of that profession. Okay, so is, for example, being a professor less prestigious than being a federal worker, and we're going to use different features to account for that. So before we jump into that, let's again, if you need to install the package, install it. Otherwise, I mean, I'm just going to use the library. So let's just look for the library CAR, and then let's view the prestige dataset, which is here. And basically, the prestige dataset, as you can see here, you're going to have in each row, you're going to have the name of a profession, and then the independent variables that we have are variables like education, income, percentage of women, prestige, census, and the type. Okay, so these are going to be the different features that we're going to use to predict the prestige. The first thing that we do, okay, that's important, it's and that's going to be common across all the exercises that you do with training and testing. The first thing you need to do is divide the dataset into training and testing sets. Okay, so how do we do that? We need to divide this in a random manner. So in this case, the manner that we are going to be that we have selected to use is basically use the remainder of the quotient. So we know that prestige has X rows. It has 102 rows exactly. Okay, so what we do is take all the rows in prestige, divide the number of row by 4, and if the remainder equals 0, that's going to be a row that we keep for the testing set. That's what the first line means. Okay, in the first line, we are basically generating row numbers that are going to be the row numbers that we use for the testing set. In fact, in the second line, you see that we are creating the prestige train dataset that has all the rows, all the columns, and all the rows but the ones in the vector test ID. And the testing dataset are going to have only the rows in the testing ID. Okay, so what we are doing here, it's really simple. It's just basically taking this table here and generating two datasets. The training dataset, which we will use to train our model, and the testing dataset, which we will use to test how good our model is in predicting prestige. Okay, and that's always how problems in machine learning need to be attacked. Okay, you first always need to divide your dataset into training and testing, and if you need to do other types of estimations, you will also have a cross-validation set. Okay, so you will have training, cross-validation, and testing. This is critical. You cannot train and test on the same dataset. That would be a mistake, and the results wouldn't be correct. Okay, so let's first, I mean, this is a code that you will probably want to save somewhere, because you're going to use it every time you need to execute something and you need to generate testing and training sets. Okay, so if we take a look at test IDX, here you see that you have 25 different numbers. Okay, and these are randomly, well, not randomly, I mean random for this type of approach. If you execute it again, it's going to be the same numbers. Okay, so we'll also look in future classes how to generate random numbers, but for the moment, let's just say that we take these ones. These rows are going to be the ones that are going to define our testing data set. Okay, so we can define a prestige test data set. That's going to have, if you take the prestige data frame, it's going to have the rows in test IDX and all the columns. Okay, so if you take a look at prestige test, you have here basically the all the columns. Let's do it. If we take a look at prestige test, you basically have all the columns. So we have education, income, women, prestige, census, and type. But the number of rows that we're going to have here are just 25, which are the rows in test IDX. And similarly, we're going to define a prestige train, the training dataset, that's going to have all the rows but except for the ones that are in test IDX. Okay. So once we have done that, okay, the next thing that we can do is basically fit a linear regression model. Okay, so we use LM, and we fit prestige, what the dot means is basically use all the other features that you have in the data frame that we are using. So instead of writing women plus census plus blah blah blah, we write a dot. And then you say, the data set that you're using for the training. In our case, you are using prestige train. Once we have that model trained, we basically use it to predict. And we predict on the testing set. And then we finally check the correlation between the data that we have predicted and the actual prestige of the data. Okay? And you can also verify whether the residuals are normally distributed or not with QQ norm and QQ line for the residuals of the model, as we said before, just to make sure that linear regression is the correct approach. So let's do that. Okay, what we're gonna do is basically we are going to create a model that's gonna be predicting the prestige based on all the other features, and the data that we're gonna be using is the prestige train. Okay. Then we are gonna use the predict function. We are gonna use the model that we have just created to predict on the new data. That's basically the testing data set. Okay. And then how can we see how good our prediction is? So we compute the correlation with the core function between the data that we have predicted and the real data. So the real data is basically go to the data frame prestige test and take the prestige column. And what we do is taking that column, so basically taking this column here in this data frame. So we are taking this column, the prestige column here, and check these values against the values that we have computed with our correlation. And we see that the correlation is really high. Okay. You can also basically save the residuals of the model, as we were saying, residuals for the model. And you can compute the QQ norm for those residuals and the QQ line. And you can see that it approximately, follows that line, although not exactly, okay? So maybe a linear regression is not actually the best approximation that we can get to the model, okay? This is how well the model is. The correlation apparently is really good, but maybe with other types of new data, we won't be doing that well. Okay. So we're gonna finalize trying to improve this model with a regularization. Okay, so it might be the case that, here we are having too many features, and some of the features might not be predictive at all of the prestige. Okay, so what we want to do is let's use regularization and try and see whether, we can improve the prediction by eliminating some of the features that we use in the predictive model. In order to use a regularization, there's a library in R. We're going to be using, there are several, but we're going to be using glmnet, so you need to load it. And then we are going to be using the glmnet command, cbglmnet command, which basically what it does, it runs a linear regression, but with a regularization. So the parameter alpha, what the parameter alpha says is whether you want a ridge or a lasso regularization, okay? And then what this model is going to do is basically just generate another linear model, but with a regularization. And then you can check the lambda value basically by checking what's the minimum value. So in CBFit, in the model that you have fitted, you can check with the $ lambda mean, and lambda mean will give you the lambda parameter that is the best lambda for the regularization. And then you can use the fitted model to predict. Okay, so you can use the prestige test dataset to predict using that model and compute the correlation. And basically what you will see if you do that is that the correlation will be better. Okay, so let's do this. But the purpose of this exercise is to see that if we train the model, fit a model with regularization, and then predict with a regularized model, and check how well the prediction correlates with the actual values, this correlation is going to be better than the previous one that we showed. Meaning that the regularization has helped somewhat to eliminate the features that were not predictive. Okay? Now, the reason why you see this in prestige train and prestige in the prestige training, the examples why you see the -4 and the -6 columns, okay, is because we are eliminating from there, first of all, the column that we want to predict. Okay, if you take a look at this here, column number 4 is prestige and column number 6 is the type. Okay, so what happens with the GLMNet function is that when you specify, okay, the data, the features that you want to use and the data that you want to predict, the format is different than with LM. Okay, remember that in LM we used to write prestige and then the features that we used to predict. In GLMNet, you need to first write the features and then whatever we are attempting to predict. Okay, so the reason why we write -4 is because the column 4 is the one that we want to predict, so we don't want it to be in the training data. And -6, we don't use it because basically the data is not numeric. Okay, and because it's not numeric, regularization won't work. And then as vector, we are basically here inputting the data that we want to predict. So let's try this. So again, in this case, what we're going to be using, we're going to be creating a CV fit. Sorry. The fit in this case is going to be a regularized fit using the GLMNet function. And in this case, the input data is first one as a matrix and as a vector, because again, this is the format that GLMNet uses. It needs to be in a matrix format and in a vector format, and prestige is a data frame, so we need to translate or transform the prestige train into a matrix. And remember that we want all the rows, but we don't want columns 4 or 6. And then we also want to add the data that we want to predict. So the dependent variable prestige train is column number 4. Okay. And then finally we want to specify alpha as being 1. So we are using the lasso penalty. Okay, so what we have just done, it's basically we have fitted a linear regression model, but with a regularization, specifically with a lasso penalty. We can plot this model, okay, and we can also plot the coefficients. So what you see here, I mean, when we plotted this model, what we are seeing here is basically the different lambda values that the model has explored. Remember that what a regularization does is that it explores different lambda values, and the lambda that gives the minimum error is the one that we end up using. Okay, and we can also take a look at the coefficients. So what you see here is that the best lambda value is going to be somewhere around 1, like 0.8 something. And in fact, you can check that value as we were mentioning before. If you take a look at the CV fit lambda mean, it should be in fact 0.86, so it's somewhere around here, the best lambda value. But as I was saying, I mean, the coefficients are also telling us something, and in fact what the coefficients are telling us is that if we want to predict prestige, the most important predictive feature is going to be the education, and then income is slightly predictive, but very, very little. And women and census do not play a role in the prediction. Okay, this is really important. This is what we have managed to do with regularization. It's basically screen out or eliminate features that are not predictive and that do not provide any type of information. Okay, so percentage of women has nothing to do with the prestige of a given profession. Okay. And then we were saying we are gonna basically try to predict with the testing set and try to find out the correlation and see whether we improve without regularization correlation. And in this case, why are we writing again -4 minus 6? Is because the matrix that we want to use, the testing set that we want to use, cannot have the feature that we are predicting, which in this case is the -4 column, the 4 column, and cannot have the 6th column because it's not a numeric value. So let's then generate that prediction. So we are gonna create a prediction using the function predict. We are gonna use the model, the fitted model, CV fit, and the new data is going to be as a matrix, the prestige test, all the rows, but without columns 4 or 6. Okay? And then we compute the correlation between that prediction and the actual data, prestige test. The column is number 4, right? Yeah, and column 4. Correlation is 0.9284. Okay? If we take a look, let me remember. If we take a look at the previous correlation where we did not have any type of regression, any type of regularization, okay, the correlation between the two values was 0.937, whereas now we are getting a correlation of 0.92. What this means in this case is that although the regularization allowed us to create, a simpler model in which we just were using one predictive feature, the the income as a predictive feature for the prestige, in reality the model did not improve. Okay, so what this means is that having other features, although they might not be very predictive, they incorporate a little bit of prediction power to the model, and they actually improve the model. Okay, so this is just an example in which we were trying to improve the prediction model with regularization, but it did not work. Okay, so the way you can look at this is that whenever you're working with a data set, always remember to divide it into training and testing sets. Always remember to train on the training set, to take the testing set to predict using the model trained, and to find the correlation between the predicted and the real data. You can also apply regularization and try to see whether that correlation improves or not. And I'll see you next week when we will be talking about logistic regressions and naive Bayes.